Windows Driver Framework. Components of a PCI driver. EvtDriverDeviceAdd event. Here we have the syntax of the event callback. As you can see, the callback accepts two arguments. The first argument, which is the WDF driver handle. The second argument, Devicelnit, which is a pointer to the WDFDEVICE data structure that is allocated by the framework. The callback returns an NT status value as well. To make use of this event callback, we need to perform these tasks. At first, we need to declare the status variable. Next, we need to declare the pnpPowerCallbacks variable. Then we need to declare the powerPolicyCallbacks variable. We need also to declare the fdoAttributes variable. Then, we need to declare the device variable. And also declare the Fdo Data variable. The developer needs also to ensure that the calling thread is running at an IRQL that is low enough to permit paging. Then, we need to set the I/O type of the Devicelnit framework structure. Then, we need to initialize the pnpPowerCallbacks variable. Then, we need to fill the pnpPowerCallbacks with desired callbacks. Then, we need to set the pnpPowerCallbacks of the Devicelnit framework structure. Then, we need to initialize the powerPolicyCallbacks variable. Then, we need to fill powerPolicyCallbacks with desired callbacks. Then, we need to set the powerPolicyCallbacks of the Devicelnit framework structure. Then, we need to initialize the fdoAttributes variable. Next, we need to fill the fdoAttributes with the desired callbacks. Next, we need to create the WDFDEVICE object that will be saved in the device variable. Next, we need to check that the WDFDEVICE object was created successfully. Next, we need to obtain the Fdo Data instance. Next, we need to initialize the members of Fdo Data instance. Then, we need to call our own implementation of the Allocate software resources routine. Then, we need to check that the call to Allocate software resources routine was successful. Then, we need to create the device interface. Next, we need to check that the device interface creation was successful. We also need to perform the WMI registration for the device. Finally, we will return the status. Task number 1, declare the status variable. As we did in the driver entry routine, here we declared the status variable and initialized it to status success. Task number 2, declare pnpPowerCallbacks variable. In the code example, we declare the pnpPowerCallbacks variable and kept it uninitialized. The variable is actually a data structure provided by the framework. The data structure is WDF pnpPower event callbacks. Task number 3, declare powerPolicyCallbacks variable. In the code example, we declared the powerPolicyCallbacks variable and kept it uninitialized. It is the data structure WDF powerPolicy event callbacks. This variable will be used later. Task number 4, declare fdoAttributes variable. In the code example, we declared the fdoAttributes variable and kept it uninitialized. This variable will be used later. Task number 5, declare the device variable. In the code example, we declared the device variable and kept it uninitialized. This variable represents a device handle that will be created by the framework later. Task number 6, declare Fdo Data variable. In the code example, we declared the Fdo Data variable and set it to null. The Fdo Data variable is a pointer to the Fdo data structure. This data structure should be implemented by the developer. We say that it is driver-defined. We will discuss it later. Task number 7, ensure that the calling thread is running at an IRQL that is low enough to permit paging. In the code example, we call the paged code macro. The paged code macro checks that the calling thread is running at an IRQL that is lower than or equal to the APC level. Please don't panic if you did not grasp the meaning of IRQL or paging, as I will discuss these details in the coming video series. Please keep in mind that a call to this macro should be made at the beginning of every driver routine that either contains pageable code or accesses pageable code. It is a best practice. It is also very important to note that if the code subsequently raises the IRQL, the macro will not detect this change. Task number 8, set the I/O type of the Devicelnit framework structure. To set the I/O type, we need to use the WDFDEVICE set I/O type method. The method in question sets the method or preference for how a driver will access the data buffers that are included in read and write requests for a specified device. As you can see, the method accepts two arguments. The first argument, which is the Devicelnit framework structure. The second argument, that is an enumeration. The provided values are undefined, neither, buffered, direct, buffered or direct, or maximum. This value defines how communication will be performed with our hardware device. Task number 9, initialize the pnpPowerCallbacks variable. To initialize the pnpPowerCallbacks variable, we need to use the WDFPnpPowerEventCallbacks init function. The function accepts as a parameter a pointer to the callback structure. Task number 10, fill the pnpPowerCallbacks with the desired callbacks. The pnpPowerCallback structure has multiple event members. As you can see in the code example, there are events related to hardware preparation, hardware releasing, D0 entry, D0 exit, and others. These events may need to be implemented by the developer. We will discuss in the future videos these events in more details. Task number 11, set the pnpPowerCallbacks of the Devicelnit framework structure. In this task, we register the pnpPowerEventCallbacks. The callbacks will get automatically invoked by the framework when necessary. Task number 12, initialize the powerPolicyCallbacks variable. To initialize the powerPolicyCallbacks variable, we need to use the WDFPowerPolicyEventCallbacks init function. Task number 13, fill the powerPolicyCallbacks with the desired callbacks. As you can see in the code example, the powerPolicyCallback structure has multiple event members. Among these members, we have arm wake from S0, disarm wake from S0, wake from S0 triggered, and so on. I will explain these events in the coming videos. Please don't panic if you don't grasp their meanings. Task number 14, set the powerPolicyCallbacks of the Devicelnit framework structure. In this task, we register the powerPolicyEventCallbacks. To do this, we need to use the WDFDeviceAdd set powerPolicyEventCallbacks method. Task number 15, initialize fdoAttributes variable. To initialize the fdoAttributes variable, we need to use the WDFObjectAttributes init context type macro. The macro accepts two arguments. The first argument, which is the address of the fdoAttributes variable. The second argument, that is a structure name, in this case fdoData. The fdoData structure is driver defined, so it should be implemented by the developer. Task number 16, fill the fdoAttributes with the desired callbacks. In the code example, we set the event callbacks as well. In this case, we set the cleanup callback event. Task number 17, create the WDFDevice object that will be saved in the device variable. To create the device object, we need to use the WDFDeviceCreate method. The method accepts three arguments. The first argument, which is the address of the device init variable. The second argument, the address of the fdoAttributes variable. The last argument, that is the address of the device variable, that will receive a handle to the newly created device. The method returns a status value that needs to be checked. Task number 18, check that the WDFDevice object was created successfully. To check that the object was created successfully, we need to use the NT status macro. The macro will return true value when the creation is successful, otherwise the macro returns false. Task number 19, obtain the Fdo Data instance. To obtain the Fdo Data instance, we need to use the fdoGetData function. We will discuss this function later. We store the result of the function call in the fdoData variable. Task number 20, initialize the members of the fdoData instance. In the code example, we suppose that the fdoData structure has a member called WDFDEVICE. Here we can assign values to the structure members and initialize them as we want. Task number 21, call our own implementation of the Allocate software resources routine. The developer should implement his own routine that will perform the allocation of the software resources. We will discuss software resource allocation later in the future videos. Task number 22, check that the call to the Allocate software resources routine was successful. The developer should check that the allocation of the software resources was successful. In the code example, we suppose that the check is based on the NT status value. Task number 23, create device interface. To create the device interface, we need to use the WDFDEVICE create device interface method. The method accepts 3 arguments. The first argument is the device handle. The second argument is a pointer to a GUID variable, also known as globally unique identifier. The GUID is the identifier of the device interface. You can see that the GUID variable was defined by using the define GUID macro. Task number 24, check that the device interface creation was successful. To check that the device creation was successful, we need to use the NT status macro. I think that you are familiar with the usage of this macro, as I mentioned it multiple times in my video. Task number 25, perform WMI registration for the device. To perform the WMI registration, the developer should implement his own registration routine. We will discuss in the future the WMI registration. Task number 26, return status. We finally need to return the status value. Summary. This summary shows the tasks that needs to be done. At first, we declare the status variable. Then, we declare the pnpPowerCallbacks variable. Then, we declare the powerPolicyCallbacks variable. Then, we declare the fdoAttributes variable. Then, we declare the device variable. Then, we declare the fdoData variable. Then, we ensure that the calling thread is running at an IRQL that is low enough to permit paging. Then, we set the I/O type of the Devicelnit framework structure. Then, we initialize the pnpPowerCallbacks variable. Then, we fill the pnpPowerCallbacks with the desired callbacks. Then, we set the pnpPowerCallbacks of the Devicelnit framework structure. Then, we initialize the powerPolicyCallbacks variable. Then, we fill the powerPolicyCallbacks structure with the desired callbacks. Then, we set the powerPolicyCallbacks of the Devicelnit framework structure. Then, we initialize the fdoAttributes variable. Then, we fill fdoAttributes with desired callbacks. Then, we create the WDFDEVICE object that will be saved in the device variable. Then, we check that the WDFDEVICE object was created successfully. Then, we obtain the fdoData instance. Then, we initialize the members of the fdoData instance. Then, we call our own implementation of the Allocate software resources routine. Then, we check that the call to the Allocate software resources routine was successful. Then, we create the device interface. Then, we check that the device interface creation was successful. Then, we perform the WMI registration for the device. Finally, we return the status. The EvtDriverDeviceAdd event is important because it allows us to register the plug and play and power event callbacks. Register the power policy event callbacks. Create the framework device object. Allocate the software resources. Create the device interface. Perform the WMI registration, Windows Management Instrumentation.